All right, so welcome to the, well, I was going to say welcome to the neuromorphic integrated bioelectronics class, which is true. That's the class we have here.
I thought we had
Well, yes, it's a class, but also very excited that we co-locate the class with our joint INC, Institute for Neural Computation, and IEM, Institute for Engineering and Medicine, Neuroengineering Seminar. And so today we're very delighted to have with us again, so Carmen Amo Alonso, who gave a wonderful talk last Friday. In fact, we also had a great Rockwood seminar by John Doyle. A few words I'd like to say before I introduce Terry, who will introduce the speaker. So this class is about neuromorphic integrated electronics, and it's not a coincidence that we co-locate this seminar, because sure enough, at Caltech also we have this field of neuromorphic engineering that was launched by Carver Mead on the premise of the physics of, foundations, right? The computation and it's all linked together. And so there, the premise in neuromorphic engineering is that distributed intelligence, like large-scale distributed intelligence, gives not only great performance, but also great resilience and great efficiency. And it just so happens that in control here too. So in fact, it was wonderful to have. I met John Doyle because when I was a grad student there too, in addition to Carver Mead exciting, it was very excited to see all this great work on control. And sure enough, this distributed control has also played out very beautifully. So let's now go over it. So Terry, you continue the introduction. So.
Okay, just to follow up as a footnote, I did a sabbatical at Caltech and went to all of Carver Mead's lab meetings. It was called Carver Lab, and all the leaders in the field were trained by Carver here in the United States. But there's a lot of excitement now because we desperately need to have more efficient computing for AI, and this is where it's going to come from. But how many of you did not go to Carmen's lecture on Friday? Put your hand up. Okay. Well, I'll give a very brief intro, which is that she comes from Spain, hails from Spain. Her degree is in aeronautical engineering. Originally, before she came here to Caltech, where she did her PhD with John. And she tells the story, or actually John tells the story. Apparently he didn't know this, but Carmen told me that she was taking all these aeronautical courses, and she took a control course from John, and it was the coolest thing she'd ever seen. So that's what you decided to do. Apparently John was a Pied Piper. Okay, well, here's a question. What would an angel look like if an angel descended into our midst? Well, the angel would be charming, have a dulcet voice, and know some control theory. After all, an angel has to control those wings, right? I give you Carmen.
Thank you so much, Terry. Thank you so much for coming. And if you came on Friday too, welcome again. Thank you so much. So today we're going to go over some of the math that we need if we want to be serious about doing language technologies and bringing control in. So today's going to be a little bit more mathy than it was on Friday. And I want to start us off. It's not working. Is it working? Okay. I want to start us off again with the plantation that we had on Friday. And if we wanted to control this plantation, say that we want to minimize the cost of the water we're spending and the energy that we spend on moving the gates, and we want to do that staying within the constraints. So as we saw on Friday, we don't want to overflow, but also we don't want to have such a low level that we don't get to water the plants. And we also saw on Friday that we do this with a controller. So the way we do this is we measure the water level, And the controller tells us how we have to actuate the gates to regulate this water level. And we do that by taking into account the considerations that I just mentioned. So we want to minimize the cost. And now we're writing this a little bit more mathematical than we did on Friday. We want to minimize the cost, and we want to subject that to the plant dynamics, because ultimately we want to account for the dynamics that we had originally. And we want to stay within the constraints. So we want to also account for the constraints on the water level. And we want to account for the initial condition for where we start, the measurement that we just took. We also want to put that in there into the optimization. And the usual way of solving this problem is with this method that's called model predictive control. And the way it works is the following. So we, actually, let me before I do that, let me show you mathematically. This is how we write it. So here I'm gonna have this cost function. I'm just asking for this function to be convex. For the dynamics of the system, this is how I'm going to write them. I'm assuming that this is a linear system. Here I have my constraints. I'm just requiring that these sets are convex. Again, that's the only assumption that I'm going to put into that. And this is how I write the initial condition. So this is how we formulate the problem that I just described mathematically. And now let me tell you how model predictive control works. It takes the measurement from the water level in this case, and it puts it as the initial condition for this for the dynamics in this optimization problem. Now, we solve for the control input, we solve this optimization problem. We have a series of inputs that we have to apply until time t, but we only take the first one, and that's the one we apply to the plant. And we keep going recursively.
By plants, do you mean the things that are in the ground?
The plant, by plant, I mean the thing in the, sorry, we call that, in control theory, we call that the plant, the blue square, the system that we want to control, that's our plant. And so this is how it would work in this setting. So this has been applied to many different systems, and this is how it would work in this setting. So here, the decision is made in the centralized controller, and then it's distributed to the different gates, and the gates actuate according to the information they receive. But the question we asked here is, what happens if we wanted for each of these gates to have agency and make their own decisions, coordinating only with a few neighbors? So what would happen if we had something like this, if we wanted our system to look something like this? And this is the case for many systems that we have to deal with nowadays, like the system, the internet, the power network, autonomous vehicles, or even the gut microbiome. Those are big networks where a system is only connected to a few neighbors. So we have to deal with these large scale networks. And something we could do is we could just say, well, whatever, we're just gonna put this network inside the system and just treat it as we normally would. But by doing that, we would, first of all, miss all the structure that the network has. And in this talk, we're gonna see that exploiting this structure is very important. And also, this would be computationally very costly and sometimes even infeasible, because we have all this distributed system, say the power network. Where do we put this controller? And also it has to do this computation that's very huge because we have so many variables. So in control theory, people have been working on this problem, and they've been developing this framework of distributed model predictive control. And in this framework, what people, the concern that people had is, well, it's very sparse. So this global information exchanges that we achieve in the centralized setting cannot really be ported to the distributed setting because of the sparsity. So they saw that as a problem. And instead, we saw that as an advantage, because we said, well, that's actually a good thing, because if I set the problem right, the sparsity is gonna let my subsystem I only talk to the neighbors and be agnostic to the fact that this is a large network. So we're using the sparsity to our advantage when it was before seen as a drawback. And the size of this neighborhood, so now if I'm subsystem I just need to receive information from systems in my neighborhood. And the size of this neighborhood is a design parameter that we can choose that we denote as D. And here is how we're going to constrain our subsystem I to only talk to the neighbors. So we're gonna say the state and the input for this system is only gonna be a function of the state, the input, the model, and the disturbance of anything in the neighborhood, but nothing outside of it. So by imposing this constraint, we're taking advantage of the sparsity, because we're saying now this subsystem is only going to depend on what happens in this neighborhood and nothing else. So we have to bring that constraint into, and we call this framework distributed and localized model predictive control. So just by doing that insight, just by bringing in that constraint, we're able to develop a framework that has robustness, scalability, and guarantees, that has global optimality and hardware efficiency, and that has lower data requirements. And we're going to talk about how all of that's possible. And there's all the different papers that show that too. So let me tell you first distributed synthesis and implementations, which is the backbone of the approach here. And then we're going to talk about the guarantees very briefly, because when you have a control system, you want it to have guarantees. So I'm going to tell you about how we're able to provide guarantees to this approach. We're also going to talk about how this approach can be globally optimal. So basically, by putting in the constraints and constraining my subsystem to be in this neighborhood, I'm not missing out on performance. That's going to help me put this into GPU and compute this efficiently. And also I can do this, all of what I told you about, in a data-driven way. So I don't need a model for the system. So let me tell you about how the backbone of this works. So how am I able to put in these constraints into the problem, and why does that let me distribute the problem? And there's two approaches, like there's two aspects of this problem. First of all, we need a distributed and localized implementation. And when I talk about implementation, I'm asking the question, how can I go from a centralized controller, big centralized controller, to a lot of smaller subcontrollers, and have them all coordinate and achieve this global policy? But how can I sign all of this subcontrollers? So that's the question of implementation. Then we also have the question of synthesis, that asks the question of how can I go from this big optimization problem that has all the variables to different sub problems that solve for each of the subsystems. So this one here is a mathematical question, and that one is an implementation question for the controller. And we need to solve both if we want to have fully distributed approach. So let's go back to what we had. And I said that the main insight from the approach was that now a subsystem, I'm taking advantage of this sparsity, so now a subsystem only needs to talk to its neighborhood, nothing else. And I said that's very easily put in the locality constraints. So usually what happens when you solve an MPC problem is you're solving for a policy. So you're solving for the U input to be a function of the state and the past inputs. So, and people have been trying to leverage this policy to the distributed setting. So they've been trying to extend the methods from the centralized approaches into the distributed ones by leveraging that policy, but that turned out to have a lot of strong assumptions. They've also tried this other approach of parameterizing this policy in a different way, and that's what we're gonna do. But so far, their methods were not scalable. So thankfully, our methods are scalable, and I'm gonna talk about that. And so we need to, I said the key to this approach is to bring in the locality constraints. So we're gonna put that into the policy, and we're gonna put that into this gamma function. So now the gamma is gonna look like that. And if you remember, this is the exact same constraint I had when I said, well, now this Sphinx subsystem only needs to talk to its neighborhood. That was the key constraint that enabled that. So we're gonna put that directly into the policy. And now we just need to solve this. And now if we solve this, we're done. But the problem is, how do we solve this? And solving this problem it's not easy, because if you know anything about optimization, we're restricting the dependencies of or decision variables. So it's not clear how to solve that. You need some specific parameterization, and we're gonna make use of the system level synthesis parameterization to solve this. And so let me give you a very quick tutorial on the system level synthesis parameterization. So if you have a control system, a closed loop system, you can write its dynamics in this way. And just for simplicity, I'm gonna go all the way until time t. From time equal 1 to time t, I'm gonna write it down, and then I'm gonna organize it in this matrix form. And this is how I can alternatively write the dynamics. So this is just notation. I just choose to write the dynamics in this way, and it's gonna come clear why in a second. I can do the same thing for the controller. So now the controller, this is a convolution over the state. So if I were to write this down for every time t, I'm gonna have something that looks like this, where the k is block lower triangular, and I can just replace this equation by this other one in matrix form. Again, this is just pure notation. And what the system level synthesis framework does is it says, well, I don't want to make the distinction between what the controller is and what the plant is or the system is. I just care about what the closed loop behavior of the system is. How does my system behave once the controller is plugged in? So this is what the system level synthesis framework cares about. And instead of having this distinction of plant versus controller, I only need to care about these two closed loop maps, phi x and phi u. So these are the new equations that are gonna describe how my system behaves, as opposed to this other two ones that we had on the left for you that was making the distinction between plant and controller. And the structure of this maps is a block lower triangular as they were for the K, for the controller. And the question that could come up here is, well, how do you know that this equations on the right are capturing anything about the system, the blue system on the left? And here's where the SLS theorem comes into play, because it tells us, well, if like this subspace, when the closed loop maps live in this subspace, and this affine subspace, they're parameterizing all the possible system responses of the system. So this is enough. We know that if we put that constraint in, we're capturing the dynamics of the system. So now what we can do is we can go back and literally just perform a change of variables. So we know that we can write the state as a map from the disturbance, and same thing with the input. So we can go into the formulation that we had before and just literally perform this change of variables. So this is what the cost and the constraints are going to look like. And I'm just replacing the state and the input by these maps here. And now for the constraint, if you remember that constraint, and this constraint right here was the constraint that was capturing the dynamics of my system, the evolution of my system. And by the SLS theorem, we know that when the maps sit in that subspace, they are already capturing the dynamics of the system. So that's enough. I can do that. But I still haven't told you how this parameterization can help me with the locality constraints. So we can do that now. So we can go back, and the second statement of the SLS theorem says that this controller achieves the desired response. So this is important because that's telling us that the closed loop responses are the structure that we put in the closed loop responses is going to translate into the controller. And the reason for that is you see the controller there, and we can implement the controller in this way, where phi x and phi u appear there directly. And the reason why that it's important is because, again, phi x and phi u, I'm optimizing over them. They're my decision variables. So I can choose the structure that I want for them, and that structure is going to directly translate into the controller. So let me explicitly show what that looks like. So we said because we're an MPC, And it would apply even if we weren't in this setting, but just to make it simpler, because we're in this model predictive control framework, we're only taking the first input that we apply to the system. So that means we only need to worry about that one matrix over there. So I'm gonna write it out explicitly. This is my matrix. And if I have a 3-node network, it's gonna look something like this. So now what I can say, if I wanted to distribute this controller, what I could do is I just apply each of the rows to each of the systems. So for example, a subsystem green only needs to compute input U1, which means it only needs access to X1, X hat 1. And so it can get away with just implementing that little green row. And the same thing goes for every subsystem. The problem here is that because they need to multiply this vector, the yellow vector, they need this global communication exchanges. So subsystem green needs to retrieve information from the blue subsystem, so the X hat 3, in order to compute its input. And the same thing goes for everybody. So you can imagine if this were like a longer network, the green subsystem would need to talk to everybody. And here is where this statement comes into play. The structure imposed on the maps Px and Phu translates to structure in the controller, because again, these are my decision variables. So I can choose the structure that they have, and I can just set these components to be 0. And if I do that, then I don't need this communication link anymore. And now, of course, this needs to be feasible. If the plant is, if those subsystems are dynamically connected, then I'm not going to be able to do that. It's going to be infeasible. But in very large networks where I have something that's sparse to begin with, I can get away with this kind of constraint. So I can set to 0 many components, and that's fine. And so these are the locality constraints. So I really want to emphasize here that just by setting some components to 0, I'm achieving precisely what I said I wanted to do at the beginning of the talk, which was I am making sure that my subsystem does not depend on anything else outside its neighborhood. So in this case, green subsystem does not depend on blue subsystem. And I achieved that, I've created that neighborhood, and it was as easy as just setting some components to 0. So we can go back and replace that constraint by the locality constraint, which is just zeroing out things. So that's easy. And I just achieved the distributed and localized implementation, because we can implement the controllers in the way I just described, and that is localized in nature. Do you have a question?
Do you forcefully set it to 0, or do you find that you can't set it to 0?
I set it to 0, and then I check whether it's feasible. But we can talk about, yeah, what size of the we need. Yeah, I can talk about that later. Yes.
You have a characterization of feasibility?
No, I don't. I only have one result that tells me when the D that you choose is as optimal as if you didn't have locality constraints, and I can talk about that, but I can comment on that later. Yeah. Yes.
What if your neighbors, for a specific agent I, your neighbors are changing over time? Because as you move along your trajectory, because you might lose your communication with some specific neighbors, and then you may create another communication with another agent. So do you have that kind of time varying communications with neighbors embedded?
No, so everything I'm describing here is for a fixed topology. I don't have a changing communication topology. I think you could put in a changing communication topology, and most things would go through just fine. And the framework definitely allows for that, but I don't have that in the theory. I don't have that work done. Yeah. Okay. So now let me tell you, so we've implemented those controllers in a localized way, but now they need to solve a problem, and each of them needs to solve a different subproblem for their specific system. And so let me tell you how we can do that. Because so far, sure, we have a distributed implementation for this controller, but we only have one big mathematical problem. So it's not clear how we would go about doing this. And if we really want to be distributed, each subsystem has to have their own subcontroller, but also has to be solving their own subproblem too. And right now we don't have those subproblems. We only have this big problem. And the literature that I described earlier, the parametrizations would get us here, but then this problem was not amenable for distribution. They were stuck with this big problem, and that hinders scalability, because as you grow the size of the network, the dimension are very big, and so runtime is very high too. So we need to think about how to distribute this problem. And the first thing that stands out here is this constraint. This is the elephant in the room here, because this constraint has, if you know how to read that, it says that we need to be within the constraints for all possible disturbances that sit on a set. So at least structured, but this is a robustness constraint. We need this constraint to hold for all disturbances in that set. So let me very briefly, I'm not going to go into the details, but very briefly tell you how we tackle that. Before I do that, let me change variables, and I'm just simplifying notation here. I'm not doing anything. I'm just going to stack whenever you see phi x and phi u, I'm just going to stack them and call the whole thing phi, because that's just convenient for the method I'm going to do now. So I'm going to do that. And now let's think about this robustness constraint. So these are the different cases. Of course, this cannot be solved all the time, like for any W set, because if set is just like any set, then we don't have the structure that we need. So I can solve that for 3 different cases. I can solve that when the set W is empty, meaning I have no noise, in which case the answer is very easy, like it just goes through just fine. We don't have disturbances, which means we're crossing out a lot of the terms of this block lower triangular matrix. So we're doing that. So that's nice, because then computationally this is much nicer to work with. We also have another case that we can tackle, and that is when we have the noise be a polytopic set, and we also have the constraint set be a polytopic set. In that case, we can also solve, like with that constraint, it translates into this other constraint. You can get to that by a duality argument. And notice that we're introducing yet another variable. So if in the previous case, we were crossing out a lot of the terms of phi and making it smaller, making it just a block column, here, not only we have to deal with the whole phi, but we also have an additional variable that's of the size of phi. So that we're gonna pay a computational cost by doing this, and we'll see that in simulation. But it's nice because we can solve the robust case, so that's fine. And we also know how to tackle yet another case, which is we have locally bounded disturbance. So at each subsystence, the disturbance that it's going to hit is bounded by some norm. And the constraints are polytopic. So if we do that, we get something like this. The constraint translates into something like this. In this case, we have to put up with the whole phi, but we're not adding any additional variables. So computationally, this is nicer than the case in the middle. And we'll see how that shows up in simulation. But just to simplify the argument, I'm going to get rid of the robustness and go through it as if it was the nominal case, like the simplest case. And then I'll tell you what happens when you put in the robustness. And I'm going to make the following assumption here. I'm going to assume that if I'm a subsystem, the cost that I need to solve for and the constraints that I have to solve for only depend on my state and my input, but nothing else in the network. So my cost and my constraints do not depend on my neighbor's state or my neighbor's input. They only depend on my state and my input. And that assumption is really going to make things easy. In our work, we've extended this to the case where cost and constraints can also depend on the neighbor's states and inputs, but I'm not going to go into that in this talk. It's not that hard, but notation-wise, it's not the nicest. So when I make that assumption, what happens is something like this. I have, so this is how we write, so the state can be written as this multiplication of the map phi times the initial condition. And so if my state only depends on me, and I have this 3-node network, meaning my state, I have the first state, I'm the green subsystem, that means I have the first column, the first row of the matrix phi. And if I'm the second subsystem, then I have the second row of this subsystem. And the same thing for the third subsystem, which means if my cost only depends on my state, that means my cost only depends on the corresponding row of this phi matrix. So that's nice because I can write things in this way. I can separate the cost in this way. And that's just by assumption. So this has become row-wise separable. Now I also have this constraint, and this constraint, by the way matrix multiplication works, we have something like that. So if I were to somehow want to separate this computation and assign a bit of this computation to each of the subsystems, the best I could do is to separate it in columns. So the first subsystem would check that this matrix times its column is equal to the first column, the second subsystem, the second column, etc. So that's the only way I have to separate this computation. And I would, so I could do that. And this has become column-wise separable. So now I have row-wise separability, column-wise separability, and that has become a partially separable problem. And the standard way to solve this is through a distributed optimization algorithm that's very popular, and it's called ADMM. So in ADMM, I don't want to give a lot of details, but basically what happens, the setting that you have is you're optimizing over 2 decision variables, X and Y, and they're only coupled through an affine constraint. And if you have that, then you can break down your optimization by an optimization in terms of just X, an optimization in terms of just Y, and then like a Lagrange multiplier step, like this linear step. So we've applied ADMM to this problem. It's not the best algorithm one can use, and there's people looking into improving this, but so far this is the algorithm we're using. So let me tell you how we use that. The first thing I'm going to do to that problem is to add an additional decision variable. By doing that, I have something like this. And now if you look at the structure of this problem, there's like phi and psi are only coupled through the last constraint. I'm making psi be in charge of the column-wise separable constraints. Phi is in charge of the row-wise separable constraints. So this problem is totally separable in terms of phi and psi, and they're only related through an affine constraint at the very end. So that makes my problem amenable for ADMM, so I can break it down into the steps of ADMM. And what's nice here is that the first subproblem, the rows of the first subproblem, so if basically now I can separate it. So the first subproblem, I can go ahead and assign each row to each of the subsystems. And now if I'm a subsystem and I get a row, a lot of those elements are going to be 0. Because if I'm a subsystem, I'm imposing locality constraints, which means I only talk to my neighbors, and everything else, all of the other entries that correspond to me talking to somebody outside of my neighborhood are going to be 0. So that means that the row I'm going to have to solve for is very small. And same thing for the columns. The locality constraints are making these problems very small. So that's the advantage of setting locality constraints. So it looks something like that in the notation of the paper, but this is basically saying that the subsystems don't even have to solve for the full row, only for the components that are non-zero, and those are very little because of the locality constraints that set everything to 0. So this is what happens when you do bring back the robustness. You have bigger decision variables like you see there, but everything else just goes through the way I explained. So now let me show you graphically what this algorithm looks like and how these subsystems have to talk to each other in order to solve this MPC problem. So green subsystem, because of the locality constraints, it doesn't talk to blue subsystem at all. So it solves the problem in this way. The first thing it does, it computes its corresponding row. We've divided row, the phi in rows. So it's only in charge of the green row, and it solves that part of the problem. It solves that optimization for its row. And as you see, small, it's only 2 components, not 3, because it's not talking to anything outside of its neighborhood. And the next thing that happens is that they have to exchange information. So it exchanges information with the pink subsystem, which is its neighbor, in order to build their column. So it's trying, green subsystem is trying to rebuild the column, the first column of phi, and pink is doing the same thing to rebuild the column. The reason why they need the column is because now they're going to compute the column-wise part. And so now they're in charge of solving for psi, and they have to solve for the corresponding column, and they need the previous information in order to solve for that. So it looks something like this. And this is, we managed to get this into a closed form, which is faster to solve the non-optimization problem. So so now green is solved, it's with the information it retrieved from its neighbor, it's solving for the column. And now again, it shares information with the neighbors. So they share information to reconstruct the row. So again, green is trying to reconstruct the first row of the C matrix, which is going to be needed in the next step. And now they perform the last step of the ADMM algorithm, the Lagrange multiplier, and they keep going recursively. And so in this way, we not only know how to build those little controllers that are distributed for each of the subsystems, but we also know how to perform the computation, enabling for this communication exchanges that only happen at a local scale, so that the computations also occur in a locally for each of the subsystems. So we have something like this, which is what we wanted. And I can show you now some experiments of how this works. So we have this network. They have this dynamics, which is like swing dynamics, and we were trying to model the power network here. And we're looking at the evolution of this node. You see here that the evolution of this node on the x-axis, we have time. On the y-axis, we have phase and angular velocity. And we also drew the constraints. And it satisfies the constraint no problem in the noiseless case. But now we have what happens when we put in noise. So when we put in noise, the nominal approach doesn't work. And we have to bring in all of this extra components of the phi matrix in order for this to stay within the bounds. The noiseless one would violate them. And the same thing when we have polytopic noise. So this is the algorithm we have that I showed you. And I said that solving this problem was okay. For the distributed implementation, it had been done before, but the scalability was really a problem. And we managed to solve this problem. Here we have the number of subsystems in the network, and we have the average runtime that each iteration, so once the cycle is completed and it's converged, how much time does it take? And it's normalized per state. So the nominal case, the one where we were crossing out a lot of the terms because we didn't have noise, it's pretty fast. The one where we have to account for the full phi matrix is a little bit, takes a little bit more time. And when we have to, when the robustness requires us to bring in yet another variable, then it takes more time. But the punchline here is that it sort of flattens out as we increase the number of subsystems, which means runtime is scalable. I can plug in as many subsystems as I want, and it would take me just as long to run this algorithm. And this is what happens if you do it in a centralized way. So if you don't distribute things, you just put everything into a laptop and let it run. This is how it would scale with the size of the network. So if it doesn't scale with the size of the network, what does it scale with? So it scales pretty badly with the size of the localized region. So now runtime does not depend on how big the network is, but it does depend on how big my neighborhood is. That's really going to be the driver. And the reason for that is that we're zeroing out a lot of the components that are not in my neighborhood. So if I make my neighborhood big, that means I need to compute a lot of things. So that's why that's the case for the scalability. And then for the runtime, then the next plot, we have horizon length, which is how much more ahead am I looking, and that also drives scalability. Not as much. It scales quadratically with the size of the neighborhood and linearly with the size of the horizon. Yes.
Sorry, so is the distributed optimization for each iteration of ADMM still in synchrony, or can they be desynchronized? Like if a central agent, which is highly connected, needs to wait for all of these neighborhoods it's in to get its full column, can one like disjointed neighbor, which it's only one you're connected with, keep iterating ADMM while this one does only one iteration of ADMM, or do they both have to be one iteration at a time?
So because they have to retrieve information from the neighbors, it just ends up happening that they all coordinate. Yeah, so they do have to wait.
In some sense, full exchange of information between the network, even if everything's not connected directly.
There's this full exchange happening, but only at the local, like exchanges only occur at the local level. But yeah, they have to wait. And if you see here, it does scale a little bit. That's the reason. Yeah. Yes.
Going back to the neuromorphic analogy, right? It's like pixels in an image sensor, right? And they exchange information to their neighbors, but not across entire system.
Yes.
So the bigger the neighborhood, the worse the time, computational time.
Yes.
But still, it's like it enhances feasibility of the problem, I guess, right? So if the original central problem is feasible, the smaller the neighborhood I take, the less the probability of feasibility.
That's right. The smaller the neighborhood you choose, the less likely it is to be feasible, because you're tightening and you're not only putting in that constraint, but making it more stringent. Yeah.
So do you have anything to say about what's the level of connectivity that will guarantee feasibility for the problem?
So we haven't looked into that, but I can tell you in practice, so I don't have a mathematical result for that. I can tell you in practice that at the very least, you have to be connected to everyone that you're connected to dynamically. So if there is a dynamic link, so if in the A matrix you have a non-zero, you definitely need to have a non-zero for those two subsystems to talk to in the closed loop. And those subsystems and at least the boundary. So we're going one more beyond that. That's what we've seen. Needs to for sure happen, but I don't have a guarantee for that, so it might be bigger. Yeah, it really depends on the system, but I'm going to comment on the size of the neighborhood later. Yeah. Okay. So that's what we
just go back for a second.
Yeah.
Why does the poly noise an order of magnitude or more take longer? There's something about that type of noise.
Yeah, because that type of noise requires when you handle the robust constraint, it handles you to put in an additional variable. So not only we have phi now, but now we have another variable that's just the size of phi that we also have to solve for. So that's why, and that doesn't happen in the other noise just because of the structure of the noise.
Problem only with distributed control, or a regular controller would have the same problem with poly noise?
I think it depends. Yeah, because
there's the math. Make nice little balls, it's really easy. But if you give arbitrary polytopes, then you really kind of have to compute for all the facets of everything.
So
it's not a norm anymore, right? It's
okay,
a mess.
so it's a general problem, not something specific. Okay.
I've always questioned why she has it in there, but the MPC people like this because one thing that's nice about this framing is just that you can add more constraints like saturations and all sorts of stuff. So you're living in this world, in the MPC world of stuff where you just want to put polytopic constraints on everything. And so I think it's natural to do that. Yeah. And so it's a little confusing because you just showed that it's so much worse, but it is intrinsically.
So these are the guarantees. So when you have a model positive control approach, people always ask for guarantees, and you do want to have some guarantees for things to ensure that some things happen. And this is the things that you want to happen. So you don't want, because you're only looking so far ahead, you don't want to cut yourself into a place where you cannot solve for the next iteration. You are just not recursively feasible. So graphically, you could think of something like that. You just get stuck, and even if you keep going, like there's no way for you to leave that region. So you want to guarantee that that will never ever happen, and you will always be able to solve for the next iteration. That's one of the guarantees you want. The other guarantee you want is, even if you're feasible and you can continue, you don't want to be oscillating up and down. You want to be asymptotically stable. So you want to just smoothly follow, like track something that's stable. So how do we compute that? I'm not going to get into the math because that's going to be a little bit hard to follow, but you're welcome to look at the paper. Let me know if you have questions. But I do want to give a little bit of a flavor of what that would look like. And this is basic control theory for MPC. So there's this theorem that says if the terminal set, so this set, is a control invariant set for the system, then recursive feasibility is guaranteed. So the system here is the dynamics and the constraints. And now I want my terminal set to be a control invariant set. So if I can guarantee that this set is a control invariant set, whatever that means, then I guarantee this recursive feasibility. And we were able to do that. Now, computing control invariant sets it's hard, especially in a distributed setting, because it scales. It's a problem that scales very badly. So we were able to, thanks to the locality constraints, compute that in a very nice way and provide a solution to this problem. And I'm going to show you in simulation why that's nice. So we're able to guarantee recursive feasibility. And now for asymptotic stability, there's this other theorem that says, basically, it's a lot of conditions. So the cause has to be continuous and positive definite. That's our choice. The constraints have to contain the origin and be closed. Again, that's our choice. The terminal cost has to be robust invariant, which again, we just talked about. And then the other condition that they put is on this terminal set. So this terminal set has to be a Lyapunov function on the terminal set. And we also, so when in order to make this a Lyapunov function, we need to break some of the assumptions that I explained to you at the beginning. So then we had to extend our framework a little bit more so that you talk to the neighbors a little bit more. But there's more communication exchanges that are required. But other than that, it goes through just fine. And yeah, I'm not going to go through the mathematical details, but I just really wanted to give the intuition. What ends up happening is something like this. So we're able to compute the terminal set offline, and it's really the biggest set you could compute. So it's really non-conservative. Usually, what would happen in the literature before is either people compute this online to try to make it non-conservative, but then you're putting a burden on your online runtime, or if you compute it offline, then you're very conservative. Because if you set your set to be the 0, then that's fine, but then that's very conservative. So our computation allows for a very non-conservative set offline. So that's nice. And we also have this distributed, like we kept the algorithm almost the same. We're only requiring a little bit more communication exchanges on the very first step. Yeah. And let me show you what this means in practice. So we run the experiments. This is the experiments that you saw already. And when you don't have guarantees, so when you don't care about what your terminal set looks like or the terminal cost looks like, then you just like are unable to continue. Like MATLAB, when you run it, it says like unfeasible. But then when you have a terminal set, it keeps going. It only like oscillates up and down all the time. And then when you also have a terminal cost, then it's nice and smooth, and then eventually smooths out. And that's true for nominal and polytopic case. And solving this problem in the robust setting was basically not solved in the distributed robust setting until this work. So yeah, and also I kept saying, oh, this is really non-conservative. And you can see here the difference between having the terminal set and not having so basically having guarantees and not having guarantees is 10 to the minus 3. So it really, we're not impacting the performance, and yet we're guaranteeing that we're able to be smooth and not be caught up in the infeasibilities or anything like that. So, and runtime wise, again, we're in the situation where computing this offline does not scale with the number of subsystems. It does scale with the size of the localized region. It's a theme in this approach. And for the algorithm, for the online algorithm, it's the same trend that you saw before. And also, if you remember the numbers, it's approximately the same. So we're really not increasing runtime here by no runtime, no performance is being impacted, and we have the guarantees. So that's pretty nice. So that's all I'm going to say about that. I'm going to talk a little bit about the locality constraints. So the question we asked here is, well, we're constraining our subsystems to just talk to the neighbors. So how do we know that this is not impacting the performance that we get at the end? Maybe if we let the subsystem talk to everybody, the performance would be better. And so what we basically found is that we found an algorithm that tells you what D is good enough so that you're not impacting performance by putting the locality constraints. Not only that, but in practice, what we found is that whenever you're feasible, whenever you can find a D, that D is always whoever you're dynamically coupled +1 plus the boundary, and that's enough and you're as optimal as if you were talking to everybody. So what that means here is that this subsystem just talking to those 3 guys is the same as if we were talking to the whole network. However, talking to those 3 guys makes runtime so much better. So that's the advantage. If we were talking to the whole network, it would take much longer to run, and it would lead to the exact same result. So our result is not for every subsystem, this is true, but if you put some assumptions on the matrix B and on the initial condition, then this holds. So that's pretty nice. And with that, and I like this result for, well, I think it gives us insight, but I also like it for the following reason. And that is, well, in that case, I don't need to have a distributed system to require this method. I could also have just any system that I want to solve in GPU. And if it just happens to have the structure that I can put in locality constraints, then I can leverage those constraints to put it into hardware. So those constraints don't necessarily need to reflect the communications going on in my distributed system. It might be enough, since putting them does not come at any cost. In some cases, I can just put them in because that's going to enable me using hardware, me using GPU. And I can tell you how and why that is. So I talked about runtime quite a lot in this talk, and even though MPC is useful in a lot of applications, it just takes a long time to run usually. So accelerating MPC is an active research problem, and particularly when you have large systems, or systems with large dimension. So what people have been doing is 2 things. Either they look at computational enhancements, so they look at how the math can play out so that it's faster, or they look at, well, just putting it into fancier hardware. But so one leads to efficient computations, and the other one leads to parallel computations. But nobody's looking at what happens if I do something to this problem, like putting locality constraints, that's not going to affect performance, hopefully, if that satisfies the constraints that the assumptions from the paper I just discussed, but it's going to come at the benefit of me being able to put this into the GPU. So we looked into this, and the only thing you need to know about GPU for this project is it has all these threads, and they run in parallel, and there's a lot of them, many of them. And these threads compute these are problems in parallel, but they have to be simple computations only. So I don't even think you can do division. Maybe you can do division, but you can't do anything beyond that. So they definitely cannot solve an optimization problem or anything like that. Just basic arithmetics. Another thing that's important to know about GPU is that the access to memory is limited. So it's not like they can all go read from the same memory. They can only read, so there's patches of threads that read from the same memory. So those can share information, but for the most part, they don't have this global exchange of information, because if you want to do that, that takes a lot of time. So there's basically the punchline is there's local information exchanges only. So this had a lot of similarities with the setting that we were discussing, which is we have parallel computations with local information exchanges only, and we tackled these problems. So in order to have the threads compute subproblems in parallel, we have to tweak our approach so that it only solves, so that we simplify the operations so they would run in GPU. So we got rid of the optimization problem basically, and we turned it into just arithmetics. And also we did something, we basically were able to mimic the subsystems in GPU just by organizing the threads in some way. And basically by doing that, we were able to, this approach is for the most part disjoint. People either focus on efficient computations or parallel computations. And so by doing this, we try to sort of bring this back together and look at how to do efficient computations in parallel hardware, and using this approach beyond just distributed settings to also account for parallel settings as well, for settings where we can get benefit from using parallel hardware without it necessarily having to be a distributed setting. So that's what I'm going to say about GPU. And now lastly, I'm just going to touch very briefly on data-driven, because I went on and on and on talking about how hard it is to solve this problem when you have a large setting, and why you can't solve this problem in a centralized way, and you need to distribute it and do all of this. But what about finding a model? So that's what we did to solve that problem. But what about finding a model to begin with for that network? That's already really hard, because this model is very big, and how do we model that? So we need to do data-driven SLS. So just very briefly, there's this Williams lemma that tells us that if we can parameterize the state and the input of my system with just past trajectories, and the matrices have to be full rank. We also, so we have something like this, and we want to translate that into the SLS framework, and that looks something like this in SLS. So the only important thing here is that we can go back and just account for that. So we're going to replace the constraint that had a model by the constraint that just contains data. But doing this in a localized way, now this becomes hard, because we put in this new G matrix there that's a decision variable, and so how to solve for that is tricky. So let me just give an intuition to on how to do that. We basically have this constraint linking phi and G, and we know that phi is localized, but what do we know about G? So the first thing we want to do is to ensure that G has some sort of locality, because otherwise, if now my subsystems have to solve for this full G, then I'm breaking the whole claim that I made at the beginning, that they only had to solve for little patches, etc. So in order to make that 0, I'm going to have to perform this computation. And so what that means is that now green subsystem has to go talk to blue, orange, and yellow in order to make that happen. So I'm going to need all of those communication links. But thankfully, we proved that it's enough for it to talk to blue, and then blue can pass on the information, and that's all we need. So that's good. We know we don't need all the communication links, and we proved that. But the second thing we need is the second thing you would think we need is, in order for this matrix with the trajectories to be full rank, we need to capture trajectories from everybody. So again, I would need to have to talk to them to know what trajectories we had all across the network in order to solve this thing and have be complete. But again, we proved that that wasn't necessary. It's enough for you to talk to people in your neighborhood, and that's enough. So we're able to put in locality constraints also in the distributed, also in the data-driven case. And the algorithm that we saw early works just as well. So we also have this working in the data-driven setting. For experiments, we showed that model-based and data-driven lead to the same results. And also the amount, so this is the amount of data that you have to collect on the y-axis. On the x-axis, we have the network size. If we were to solve this centralized, we need to collect more and more and more data the bigger our network is. But in this setting, the amount of data that we need to collect plateaus because we only need to collect data from our neighbors, that's it. So that's nice. Again, the amount of data scales badly with the size of the neighborhood. And runtime also plateaus with time. So this is, sorry, with network size. So this runtime, this is network size, and it plateaus with time. And this is the punchlines of the approach. There is many things that could be explored here. One of them being layer architectures, and John really asked me to tell you like 2 things quickly about layer architectures. So so we'll do that very quickly. We have this one paper where we looked at what happens in this network if we have a reference that we need to track. So each of the subsystems here have to track a reference, but also they have some disturbance that they need to avoid. So this is very similar to what you saw about the trail and the bumps. We need to solve these 2 objectives at once. And it turns out that solving, like layering this controller and having an MPC controller that runs every few times with an offline controller that just rejects the bumps is more efficient, but as performant as just having an MPC controller that does everything all the time. So this idea of layering the controllers turned out to work pretty nicely here. And MPC is a big enabler of this layering. So here you have, when we have basically the local MPC with the layer is almost as optimal, but it scales much nicely. You don't need to compute it as many times, and the communication is just local. So yeah, and this is what happens when you don't layer. So if you just do MPC, you're very, very costly. So green here, this is the different evolution of the trajectories and the actuation over time. And green is what happens when you do layered. You're doing as well as when you do just centralized MPC, which is the blue, which is very costly. If you just have one layer of the simple controller, it just fails. It's the red one and it fails. So it looks like layering here is the sweet spot. And that was kind of the punchline. So that's what we have. This approach is being applied. So one of my collaborators is looking into this for the internet and the power network. I applied this approach for autonomous vehicles in my internship at Tesla. And some of my colleagues that were students with John applied this for the gut microbiome. So we're excited about the applications. And yeah, that's all I have. Thanks.
Carmen, this is really impressive that you solved this problem, but you're not the first one to solve it.
Okay, the brain.
Yes.
Yeah.
So, your brain
We think that's how our brain works.
is distributed control, as John was telling you. It has layers, and it's a mystery because it didn't fit into the traditional engineering framework of a centralized controller. And now we're understanding the math behind it. This is really exciting. Now, the story, when I was a graduate student, the math department is very, very distinguished. And when they are uncertain about something, they talk to the mathematicians at the Institute of Advanced Study next door, who are even more distinguished. But who do the mathematicians at the Institute talk to? They only talk to God. I suspect, Carmen, as we know, angels do talk to God. I think that's maybe where you're getting your intuition. Okay, so any other questions? Way in the back, way in the back.
So more of an aside. So this is a very interesting formulation, and I think it can be used in the framework of optical flow estimation because this concept of locality fits perfectly there. You have your, patch of 5x5, 3x3 pixels, and you try to estimate what flow or what direction in 2D space, and invariably solve an overdetermined equation. So, you have clusters of, interesting localities that you're solving, and I think that'll be an interesting application to explore with this framework.
Oh, nice. Yeah, I don't know much about that, so I cannot really comment, but yeah, that would be great.
Yes, go ahead.
Could you talk more about how you handle noise in the data-driven case?
We haven't. No, that's a really
Yeah,
good
because
point.
the fundamental lemma breaks down.
Yeah,
noise.
exactly. Yeah, we haven't, and
So
we're
but
very
then-
eager to get some help.
So if there is no noise, what is the point of your using the SLS parameterization?
As opposed to what?
Just so from what I understood in this talk, you are including gain matrices that multiply the previous noise terms as well.
Yeah.
And if you have no noise, then
Oh.
it's just one linear transformation to the original state.
Yeah, but you still inherit that you can still put in locality constraints by lifting the dimension with the SLS parameterization. You can still put in locality constraints, so you do get all the benefits from distributed guarantees. So you still get the recursive feasibility, asymptotic stability guarantees in a local way in the data-driven setting.
Yes.
I was wondering if you had explored any results about the topology of the network, and if you could design that, if there are certain motifs or something like that, would that improve convergence or slow down speed?
Probably, like I can only comment on like the experiments that we've run, and in some when we were playing with, so we had this grid and we were setting the links at random, like the connectivity was kind of set at random, and sometimes it took longer to converge than others, especially when we had some sort of hub, and then things had to span from that. That took longer to converge, but we haven't really formally explored this.
Let me just say one thing, which was one of the very early work using SLS, not the MPC part, just the basic LSLS, was where to put wires and where to put sensors and where to put actuators when you're going to do this kind of control. It turns out it's really nicely formulated as this atomic norm regularization, very Steve Boyish, right? And so what you do is you put these regulars out there. But if you just solve a global problem, it's a mess, right? But it turns out SLS lets you decompose the design problem to be local. So you're designing your network locally, and you're designing your controllers locally, all together. And what you're just relying on is the fact that atomic norm regularization does produce sparsity in a very nice way. Now that's just kind of magic, and that's a whole other field. But that's already existing. We don't have to redo that. All this does is means the computation can be done in patches, just like everything else. And so, but that hasn't been ported over to this stuff, and it's not clear how it would, in the sense that what you'd have to do is just turn off the MPC and just do SLS in the design stage. So I think I think that it could be molded, put together with this, but that hasn't been done. So.
Okay, with that.
Hi, that was a great talk, and Friday talk was awesome as well.
Thank you.
I was wondering if you have looked at or thought about, or maybe John, using this framework in the context of actual like neuroscientific data.
I am using this for learning, so for
Right.
like transformers, like machine learning.
Yeah.
Yeah. So, but not in neuroscience.
Yeah, what happened, I'll tell you what, I can tell the story of that. The paper I talked about the device vision. So the idea for looking at that was this Anish Sarma, who's just finished medical school. So, but he had the idea to look at this. And then Lisa Lee was working on it.
Yep.
And she first did everything with SLS and got the results. And then we're going, oh God, we're going to try to bring a new bunch of machinery to a new problem in neuroscience, right?
Right.
We're already on shaky ground. We didn't have Ann Churchland, we would be on really shaky ground, but she'd already done the experiments that we knew supported what we said. So what Lisa just did was just work really hard to not need SLS. And the way she did it is she said, oh, we're just going to put delays in the periphery, not in our internal computation, not in the column fill, which is the periphery. And so we actually get this results there because you can sort of treat visual cortex as a bunch of processing on sensing with delays.
Right.
But it's kind of a hack.
Okay.
What somebody really needs to do is now full on just say, okay, let's not play games with this. Let's just do what's really there in the brain.
Yeah.
And then apply this SLS, and you're going to need the SLS to do that.
Yeah, that would be cool.
But that's, you know, this is right. This is the frontier right now.
Yeah.
Asking those kind of questions,
Yeah, of
right?
course.
That's exactly the frontier, right?
Yeah.
Yeah. And so we're getting, you know, want to get people interested in this because she's created such a big frontier. We'll never, you know, all the people that are kind of in the SLS bubble, there's just too much to do now. So we're hoping to get other people interested.
Question there?
So how do you see this as similar or different to like, local graph message passing networks? Apologies if I missed this in the first few minutes. I'm not making it quickly. So obviously those aren't constraint based, but you know, they use sort of similar. They try to make similar guarantees about needing less data because they only operate over a local region. And
I don't know that I'm familiar with this one. Can you?
Dynamics is kind of the difference with a message passing. It's usually not a dynamic systems.
Oh, I see. Yeah.
Superficial, I don't think has anything to do with this, but
we can talk about
all these things are worth looking. All these questions are worth pursuing,
I think
right?
it is, there is some overlap, though,
Okay.
because that was exactly where my mind went to. as
Okay,
well.
yeah.
they are being used for dynamics.
Yeah, yeah.
Okay, good question then.
That's the cutting edge of the graph side of research, is like the spatio.
And I'm about a decade out of date on that stuff,
It's
so.
hard to keep up with everything.
Yeah, so, no, those are good questions, and so that's, you know, that's what we're hoping people who have that domain expertise will learn a little of this and then figure out what's next.
So like people are using it for like weather prediction, for instance, to like model local regions and then have sort of like big systems that are interacting with each other. But I do think that a very unsolved problem in that domain is like how to define what the scale of the system is, defining like the layers part of it.
Yeah.
And oftentimes they're sort of predefined based on the question in terms of the domain, in terms of like what is the local message passing. But yeah, we can chat about it.
Yeah, I would love to. Yeah, and here for this layer work, that was exactly the question. Like, how do you sign the communication exchanges? It's kind of what defined what the layers were, because you need intense communication on the lower layer, but then as you go up, it's okay to just not get as much like faithful information all the time, that kind of thing. So communication is really a driver, and defining the layers also very.
Okay, let's see. Last two questions. We'll start with you.
This is kind of a silly question, but I'm just curious. So when you're comparing to like the optimization over the full network, which is the thing that you're trying to speed up, that looked like you were doing some pretty big optimization problems over big networks for the ground truth comparison. Did you just like run things for forever? Did you choose like a very clever network to compare to?
No, it was like days rapid.
Okay. Wow.
Okay, good.
Beautiful work. Now,
Thank
so
you.
this being in a class on neuromorphic integrated electronics, let me just touch on an important point here. So distributed is great, localized is great too. But now in neuromorphic engineering, you also look at distributed systems where computation is performed not in a usual digital way, right? Where you have this very localized computation, and in a parallel system, you can benefit if you don't communicate too much to your far distances. But there are ways of computing in analog that can reach long distances, almost by construction. Right? So Kirchhoff's voltage current laws that. Would this work extend in a way to systems where you may still have long range communication, cheap communication, right? Right? So that you don't have to implement this now on GPU, but you can implement it, say, on analog circuits that have these are called computing memory, right? Where the computation is like in the brain, that's where computation is performed right at the memory inside the memory.
Yeah.
And so when I'm running on GPUs, you can run on this massively parallel ML convenience time circuits.
So the way I see this is you would have yet another layer of control that would take care of the bigger communication, like the long range communication.
So that would be like the layered architecture.
Yeah.
So yeah, you could, all the heavy work will be done with spinal cord, and then you have these controllers on top, which are, maybe have more memory, and can help with the lower level.
So I think the intersection of at least this with what you do is could be really interesting. And we so think digital all this, right? But it doesn't have to be, right? It's just that what you're mostly designing is what goes on in computers, and so it's mostly digital, and so, but that doesn't have to be it, right? So I think this is kind of the tip of the iceberg of what I think is possible. But this whole shift towards localization and allowing delays and allowing all the sparsity stuff, it just changes everything, and now we have to go back and kind of redo everything.
Okay, I want to remind everybody that John Doyle is now here. And
Sort of.
he's a real resource. Okay, he's here and there,
I live here.
He lives here, which is a good place to live, but he works up at Caltech, which is a good place to work. So he has the best of both worlds. Okay, let's thank Carmen again.
Okay, can I ask a question before everybody disappears, or
Yeah.
over already?
I didn't make it a whole thing like that.
Can I?